Welcome! In this session, we'll tackle an essential and widely discussed problem in algorithmic problem solving: median of two sorted arrays. This problem tests your understanding of array manipulation and efficient algorithms, making it a staple for coding interviews. Let's dive in and explore the solutions. The problem we are solving is to find the median of two sorted arrays. You will be given two integer arrays, nums1 and nums2, which are already sorted in non-decreasing order. The size of these arrays is m and n, respectively, and both sizes are non-negative integers. Your task is to return the median of the combined values from these two arrays. The median is defined as the middle value when the numbers are ordered. If the total number of elements is even, the median is the average of the two middle values. Importantly, we need to achieve this with a time complexity of O log min m n. For example, if the input arrays are nums1 equals 1, 3, and nums2 equals 2, then the output will be a single floating point number representing the median of the combined values. In the first example, the arrays are nums1 equals 1, 3, and nums2 equals 2. When we combine and sort these arrays, we get 1, 2, 3. The median is simply the middle element of this combined array, which is 2. So the output is 2.0. In the second example, the arrays are nums1 equals 1, 2, and nums2 equals 3, 4. When we combine and sort these arrays, the result is 1, 2, 3, 4. Since the total number of elements is even, the median is calculated as the average of the two middle elements, which are 2 and 3. The result is 2 plus 3/2 equals 2.5. Therefore, the output in this case is 2.5. In the third example, the arrays are nums1 equals 0, 0, and nums2 equals 0, 0. When we combine and sort these arrays, the result is 0, 0, 0, 0. Since the size of the array is even, we calculate the median as the average of the two middle values, which are both 0. The result is 0 plus 0/2 equals 0. So the output is 0.0. Now, let's look at the constraints. The lengths of nums1 and nums2 are exactly equal to m and n, respectively. Both m and n can range from 0 to 1000, meaning one or both arrays can be empty. Additionally, the elements of these arrays can range from -10⁻6 to 10⁻6, covering a wide spectrum of possible values. The arrays nums1 and nums2 are guaranteed to be sorted in non-decreasing order. The key requirement is that the solution must meet the time complexity of O log min m n. This means we need to find an efficient approach, especially when working with large arrays. Some edge cases to consider include scenarios where one of the arrays is empty, such as nums1 equals, and nums2 equals 1, 2, 3. Another scenario is when both arrays contain identical elements, for example, nums1 equals 2, 2, and nums2 equals 2, 2. Additionally, the arrays may have vastly different sizes, such as nums1 equals 1, and nums2 equals 2, 3, 4, 5, 6, 7. Finally, we must also handle numbers at the extreme ends of the allowed range, like nums1 equals -10⁻6, and nums2 equals 10 to the power of 6. These cases highlight the importance of designing a robust and efficient solution. To tackle the problem of finding the median of two sorted arrays, we first consider the brute force approach. The intuition here is simple: merge the two arrays into one sorted array and then directly calculate the median. This can be achieved in two straightforward steps. First, merge nums1 and nums2 into a single sorted array, which takes linear time, O, m plus n. Then, determine the median of this merged array by accessing the middle element or averaging the two middle elements, depending on whether the total length is odd or even. While this method is intuitive and easy to implement, it has clear trade-offs. The time complexity of O, m plus n, may be acceptable for smaller input sizes, but it becomes inefficient for large datasets. Additionally, the space complexity of O, m plus n, adds overhead, as we need extra memory to store the merged array. Most importantly, this approach does not meet the problem's requirement of O log min m n time complexity, making it unsuitable for this problem's constraints. To address the inefficiencies of the brute force approach, we turn to an optimized binary search strategy. The key intuition here is to avoid merging the arrays altogether. Instead, we find a partition point in the array such that all elements on the left side are smaller than those on the right. From this partition, the median can be directly calculated. There are a few key observations that make this possible. First, the median depends only on the partition halves, not the entire arrays. Second, we can leverage binary search on the smaller array to achieve the desired time complexity of O log min m n. Here's how it works. Assume nums1 is the smaller array, swapping if necessary. We perform binary search on nums1 to find a partition index I, and calculate the corresponding partition index j in nums2. The goal is to ensure the partition is valid, which happens when the largest element in the left partition of both arrays is less than or equal to the smallest element in the right partition. If the partition is valid, the median can be calculated directly. For odd total lengths, it's the maximum of the left partition. For even lengths, it's the average of the maximum of the left and the minimum of the right. If the partition isn't valid, we adjust the binary search range and continue. This approach is highly efficient, with a time complexity of O log min m n and space complexity of O1. However, it does require careful handling of edge cases, such as when partitions occur at the boundaries of the arrays. Given the options, the optimized binary search approach stands out as the clear choice for solving this problem. It meets the required O log min m n time complexity and avoids the overhead of merging the arrays entirely. Its space efficiency is another significant advantage, as it uses only O1 additional space. The key insight that simplifies this problem is realizing that the median relies only on the partition indices rather than the entire arrays. By leveraging binary search, we can drastically reduce the problem size in each step, making the solution extremely efficient. Of course, there are trade-offs to consider, especially the challenge of handling edge cases, such as when partitions fall at array boundaries. However, with careful implementation, these can be addressed effectively. When comparing this approach to alternatives, the brute force method, while easy to implement, is inefficient for large inputs. Other methods, such as recursive approaches or iterative merging, either fail to meet the problem's constraints or are unnecessarily complex. In conclusion, the optimized binary search approach is the most elegant and efficient solution, perfectly aligned with the constraints and requirements of the problem. To solve the problem of finding the median of two sorted arrays, we need an efficient approach since the solution must run in O log min m n time. Here, m and n represent the lengths of the two arrays. The key idea is to partition the arrays into two halves such that the left partition contains half of the total elements, or one extra if the total number of elements is odd, and the right partition contains the rest. Once we successfully divide the arrays this way, the median is simply determined by the maximum value in the left partition and the minimum value in the right partition. Now, the first step in this algorithm is to identify the smaller of the two arrays. Let's call the arrays nums1 and nums2. If nums1 is not the smaller array, we swap them. This ensures that we perform binary search on the smaller array, which reduces the number of comparisons and keeps the complexity logarithmic. After determining the smaller array, the next step is to define the partitions. Let m and n represent the lengths of nums1 and nums2, respectively. We define two partitions, partition 1 for nums1 and partition 2 for nums2. The partitions must be balanced, meaning the total number of elements in the left partition equals the total number in the right partition, or is just one larger for odd-sized arrays. To achieve this balance, partition 2 is calculated as m plus n plus 1 / 2 partition 1. We then perform binary search on the smaller array, initializing two pointers, low to 0 and high to the length of nums1, or m. While low is less than or equal to high, we calculate partition 1 as the midpoint of low and high, and derive partition 2 accordingly. To evaluate the validity of the partitions, we determine the boundary values. These include max left 1 and min right 1 from nums1, and max left 2 and min right 2 from nums2. Special cases, like when a partition index is at the start or end of an array, are handled by setting boundaries to negative or positive infinity. If the boundary conditions are satisfied, meaning max left 1 is less than or equal to min right 2 and max left 2 is less than or equal to min right 1, the partitions are valid. Otherwise, we adjust the binary search. If max left 1 is greater than min right 2, we decrease high by moving it to partition 1 1. On the other hand, if the boundary condition fails because max left 2 is greater than min right 1, we increase low by moving it to partition 1 plus 1. Once the correct partitions are identified, calculating the median becomes straightforward. If the total number of elements is odd, the median is simply the maximum of max left 1 and max left 2. However, if the total number of elements is even, the median is the average of the largest element in the left partition, which is max left 1, max left 2, and the smallest element in the right partition, which is min right 1, min right 2. This approach ensures that the median is calculated directly from the boundary values of the partitions. The algorithm leverages several key insights. First, properly balancing the partitions guarantees that the median can be found without merging the arrays. Second, performing binary search on the smaller array minimizes the number of comparisons, keeping the time complexity logarithmic. Additionally, edge cases like empty arrays are seamlessly handled by setting the boundaries to negative or positive infinity. This makes the algorithm robust and efficient, even for large input sizes. The algorithm primarily relies on the input arrays, nums1 and nums2, to retrieve the boundary values during partitioning. Since no additional storage is required, the space complexity remains constant at 1. The binary search variables, low and high, track the search space for partitioning the smaller array, which ensures that we only focus on the relevant sections of the input. In terms of complexity analysis, the time complexity is O log min n, because the binary search is applied to the smaller of the two arrays, minimizing the number of iterations. The space complexity is O1, because the algorithm does not allocate any extra memory aside from a few variables. This makes the approach not only optimal for large input sizes but also highly practical for scenarios where efficiency and memory usage are critical considerations. Here, we begin by defining a class called solution that contains a function named findMedian sorted arrays. This function takes two input lists, nums1 and nums2, which represent the two sorted arrays. The first step is to ensure that nums1 is always the smaller of the two arrays. This is important because we will be performing a binary search on the smaller array to optimize the process. If nums1 is larger, we simply swap the two arrays. Next, we calculate the lengths of nums1 and nums2 and store them in variables x and y, respectively. Following this, we initialize two pointers, low and high, which represent the search space for the binary search on nums1. The main logic of the function is implemented within a while loop that runs as long as low is less than or equal to high. Inside the loop, we calculate partition x, which is the midpoint of the current search space in nums1, and partition y, which is derived based on the total length of the combined arrays. Partition y ensures that the left and right sides of the combined arrays remain balanced. To handle edge cases where partitions go out of bounds, we use negative infinity for values on the left and positive infinity for values on the right. This helps us safely compare elements even when one of the partitions is empty. We then extract the maximum values from the left partitions and the minimum values from the right partitions for both arrays. These values are critical for determining if the current partitioning is correct. If the maximum value on the left side of nums1 is less than or equal to the minimum value on the right side of nums2, and vice versa, it means we have found the correct partition. At this point, we check if the total number of elements in the combined arrays is even or odd. If the total is even, the median is the average of the maximum value from the left side and the minimum value from the right side. If the total is odd, the median is simply the maximum value from the left side, as it lies exactly in the middle. However, if the maximum value on the left of nums1 is greater than the minimum value on the right of nums2, it means we need to adjust the partition by moving left in nums1. This is achieved by reducing the high pointer. Similarly, if the maximum value on the left of nums2 is greater than the minimum value on the right of nums1, we need to move right in nums1 by increasing the low pointer. The loop continues until we find the correct partition. Finally, if no valid partition is found, which should not happen with properly sorted input, we raise a value error to indicate that the input arrays are not valid or sorted. Here, we begin implementing the solution to find the median of two sorted arrays in Java. First, we ensure that the smaller of the two arrays is assigned to nums1. This optimization reduces the number of partitions we need to consider, as we always work with the smaller array. If nums1 is longer, we simply swap the arrays. Next, we store the lengths of nums1 and nums2 in variables x and y, respectively. The binary search range is then initialized with low set to 0 and high set to the length of nums1. Now, within the binary search loop, we calculate the partitions for both arrays. The partition index for nums1, referred to as partition x, is the midpoint of the current search range. The partition index for nums2, partition y, is derived such that the left side of the combined arrays contains half of the total elements. To handle edge cases like an empty partition, we use integer.min_value for the maximum of an empty left partition and integer.max_value for the minimum of an empty right partition. These values ensure comparisons remain valid. Finally, we calculate max left x, min right x, max left y, and min right y, which represent the boundary values on either side of the partitions in both arrays. Now, we check if the partitions are correctly placed. If the largest value on the left side of nums1 is less than or equal to the smallest value on the right side of nums2, and vice versa, then we have found the correct partition. At this point, the median can be determined based on the total number of elements in the combined arrays. If the total length is even, the median is the average of the maximum value from the left side and the minimum value from the right side. If the total length is odd, the median is simply the larger value from the left side of the partitions. However, if the partitions are not correct, we adjust our binary search. If max left x is greater than min right y, it means we've included too many elements from nums1 on the left side, so we move high to partition x1. Otherwise, we move low to partition x+1 to include more elements from nums1 on the left. If no valid partition is found, which should not happen for properly sorted arrays, we throw an exception indicating invalid input. In this example, we start with two arrays, nums1 containing 1, 3, and nums2 containing 2. Since nums1 is already smaller or equal in size to nums2, no swapping is needed. The lengths of the arrays are x equals 2 for nums1 and y equals 1 for nums2. To find the median, we apply a binary search on nums1, initializing low to 0 and high to the size of nums1, which is 2. For the first iteration, we calculate partition x as the midpoint of low and high, giving us 1. Partition y is determined to balance the split, calculated as x plus y plus 1, // 2 minus partition x, resulting in 1. We now evaluate the elements around the partitions. Max left x is nums1, 0, which is 1, and min right x is nums1, 1, which is 3. Similarly, max left y is nums2, 0, which is 2. And min right y is infinity because partition y falls out of bounds in nums2. Next, we check if the partitions are valid. The conditions max left x less than or equal to min right y and max left y less than or equal to min right x are satisfied, making the partition valid. Since the total length of the arrays is odd, the median is the maximum of max left x and max left y, which is max 1, 2, resulting in 2. The result of example 1 gives us a median of 2. Now, let's look at example 2 with nums1 as 1, 2, and nums2 as 3, 4. As before, we verify that nums1 is the smaller array, which it is, so no swapping is needed. The lengths are x equals 2 for nums1 and y equals 2 for nums2. We initiate binary search on nums1 with low set to 0 and high set to 2. This setup ensures we are ready to divide the arrays into two halves and calculate the median using the binary search process. In the first iteration of the binary search for this example, partition x is calculated as the midpoint of low and high, resulting in 1. Partition y is then determined to balance the split, calculated as x plus y plus 1, // 2 minus partition x, which gives 1. Next, we compute the values around the partitions. Max left x is nums1, 0, which is 1, and min right x is nums1, 1, which is 2. For nums2, max left y is nums2, 0, which is 3, and min right y is nums2, 1, which is 4. We check the partition validity conditions. While max left x less than or equal to min right y holds true since 1 less than or equal to 4, max left y min right x does not satisfy the condition because 3 greater than 2. This means we need to move the binary search window to the right in nums1. To do this, we update low to partition x plus 1, which is 2. In the second iteration, with the updated low value, partition x is recalculated as low plus high // 2, which is now 2. Partition y is adjusted to x plus y plus 1 / 2 minus partition x, resulting in 0. We evaluate the values around these partitions. Max left x becomes nums 1, 1, which is 2, and min right x is infinity because partition x equals x, placing it out of bounds. For nums 2, max left y is negative infinity since partition y is 0, and min right y is nums 2, 0, which is 3. Checking partition validity, we see both conditions are satisfied, max left x less than or equal to min right y and max left y less than or equal to min right x. Since the total length of nums 1 and nums 2 is even, the median is calculated as the average of the maximum of the left partition and the minimum of the right partition. This gives us max 2 inf plus min anf 3/2, which simplifies to open parenthesis 2 plus 3 close parenthesis divided by 2, resulting in 2.5. In example 3, nums 1 is 0, 0, and nums 2 is also 0, 0. We confirm that nums 1 is smaller or equal in size to nums 2, so no swapping is necessary. The lengths are x equals 2 for nums 1 and y equals 2 for nums 2. Binary search is initialized with low set to 0 and high set to 2. For the first iteration, partition x is calculated as low plus high / 2, giving 1. Partition y is determined as x plus y plus 1 / 2 minus partition x, resulting in 1. We compute the values around the partitions. Max left x is nums 1, 0, which is 0, and min right x is nums 1, 1, which is also 0. For nums 2, max left y is nums 2, 0, which is 0, and min right y is nums 2, 1, which is also 0. We check the partition validity conditions, and both max left x less than or equal to min right y and max left y less than or equal to min right x are satisfied. Since the partition is valid and the total length of nums 1 and nums 2 is even, the median is calculated as the average of the maximum of the left partitions and the minimum of the right partitions. This results in max 0, 0 plus min 0, 0/2, which simplifies to 0. Therefore, the median for this example is 0. The time complexity of the optimized solution for finding the median of two sorted arrays is O log min m n, where m and n represent the lengths of the two input arrays. This efficiency is achieved because the algorithm applies binary search on the smaller of the two arrays, significantly reducing the search space. To break it down further, the initial step ensures that the binary search is always performed on the smaller array, which is an O1 operation. During each iteration of the binary search, key calculations like determining partitions and finding maximum and minimum values on either side are constant time operations. Since the binary search cuts the search space in half with each iteration, the total number of iterations is logarithmic with respect to the size of the smaller array. Finally, once the correct partition is identified, the median is computed in constant time. Altogether, the dominant factor remains the logarithmic complexity of the binary search, leading to a total time complexity of O log min m n. The space complexity of this algorithm is O1, which means it requires only a constant amount of additional memory. This efficiency is achieved because the algorithm maintains a small set of variables such as low, high, partition x, partition y, and a few others to facilitate the binary search. These variables are updated iteratively without using any extra data structures or making recursive calls. Additionally, the input arrays are accessed directly without creating copies or modifying them, further conserving memory. As a result, the algorithm's space usage remains minimal, regardless of the size of the input arrays, making the space complexity O1. When comparing the optimized solution to a brute force approach, the benefits of the binary search-based algorithm become even more apparent. In the brute force method, the two arrays are merged into a single sorted array, which requires O m plus n time for the merging process and O m plus n space to store the merged array. In contrast, the optimized approach avoids this merging step entirely, reducing the time complexity to O log min m n and the space complexity to O1. Furthermore, the optimized approach maintains its efficiency in all scenarios, best, average, and worst cases, because the binary search always operates logarithmically, regardless of the input data. This consistency highlights the robustness and scalability of the optimized solution, especially for handling large arrays. The time complexity of O log min m n can be mathematically proven by analyzing the behavior of the binary search. Let k represent the size of the smaller array, which is min, m, n. The binary search operates on this array, and with each iteration, the search space is halved. This halving process continues until the correct partition is found, resulting in log_2, k, iterations. Each iteration involves constant time operations, such as calculating partitions and comparing values, which do not add any additional overhead to the logarithmic nature of the search. Therefore, the total time complexity of the algorithm is determined by the logarithmic reduction of the search space, leading to the final result of O log k, or equivalently, O log min m n. In this section, we'll explore some common mistakes that can occur when solving the problem, and why they lead to errors. First, a frequent issue is merging the arrays incorrectly. This happens when using a naive merging approach that doesn't account for edge cases, such as when one array is empty or when there are duplicate elements. If you don't handle these situations explicitly, it can lead to incorrect median calculations or even runtime errors. Another mistake is not considering edge cases for the median calculation itself. For example, assuming the median is always at a fixed index can cause problems, especially when the combined length of the arrays is even. In these cases, the median is the average of the two middle elements, not just one value. Lastly, some solutions inefficiently sort the merged array again, even though both input arrays are already sorted. This increases the complexity unnecessarily from O m plus n to O m plus n log m plus n. Instead, you should use a two-pointer merge technique to avoid this overhead and maintain efficiency. Now, let's focus on a couple of additional pitfalls. One common mistake is using binary search on the longer array instead of the shorter one. This approach increases the number of iterations needed to find the correct partition, making the solution less efficient. To optimize, you should always apply binary search to the smaller array, as this minimizes the number of comparisons. Another frequent issue is off-by-one errors in binary search. These errors occur when partition indices are miscalculated or the boundaries aren't adjusted correctly. This can lead to incorrect partitioning, which results in either the wrong median value or runtime errors. To avoid this, it's critical to carefully verify the partition logic and ensure that all edge cases, such as empty partitions or mismatched boundaries, are handled properly. Shifting gears, let's discuss some insights that can help you excel in interviews when tackling this problem. One key insight is that this challenge is designed to test your ability to optimize solutions by leveraging the mathematical properties of sorted arrays in binary search. The goal is to reduce the complexity to O log min m n, which highlights your ability to think efficiently. This problem also follows a classic divide and conquer pattern. Using binary search, you divide the arrays into two partitions, ensuring that all elements in the left partition are smaller than those in the right. Another important aspect is communication. During an interview, be sure to clearly explain how you handle edge cases, such as empty arrays, arrays of unequal lengths, or overlapping elements. Finally, when discussing optimization, emphasize why a brute force approach, like merging and sorting, is suboptimal, and highlight the trade-offs involved as you transition to the binary search method. To deepen your understanding, you can explore related problems, such as merging k-sorted lists or finding the kth smallest element in a sorted matrix, which share similar patterns. Finally, let's look at some alternative approaches to solving the problem, along with their trade-offs. The brute force approach involves merging the two arrays, sorting the result, and then calculating the median. While simple to implement, this method has a time complexity of O m plus n log m plus n, making it inefficient for larger inputs. A more efficient option is the two-pointer merge technique. Here, you simulate the merging process of the two arrays to locate the median directly. This has a time complexity of O m plus n, which is better, but it's still not ideal for very large datasets. The most optimal approach utilizes binary search on the smaller array. By partitioning the arrays and ensuring balanced partitions, you can find the median in O log min m n time. However, this method requires careful implementation to avoid off-by-one errors and ensure the partitioning logic is correct. Each approach has its merits, so choosing the right one depends on the constraints and size of the input. Great job! You've successfully walked through the problem median of two sorted arrays. Remember, this type of problem is valuable for enhancing your data structure and algorithm skills. Keep practicing, stay curious, and we'll see you in the next session. Don't forget to like, share, and subscribe. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!